I want to talk about polynomial division. So my goal in this video is to divide some polynomials using long division. So I want to take 4x squared plus 6x plus 3 and divide it by 2x plus 1 and find a quotient and a remainder. But I thought we'd start by reviewing division of whole numbers. As silly as that might sound, when I divide whole numbers, I'm actually arranging my work thinking about place value. The number 463 is 3 ones, 6 tens, and 4 100s. And if I think about that's kind of similar to what this polynomial is doing if I were to think about x being equal to 10. Because here I have 3 ones, right? Literally 3 times 1. If x is equal to 10, it's 6 times 10, 6 tens. Plug in x here and I get 10 squared is 100, I have 4 100s. So in plugging in x equals 10, I would get 463. 21, 1, 1, 2 x's, well if x equals 10, it's 2 tens, and I get 21. And so there's some natural connection between these two things. So here I'm thinking place value, ones, tens, hundreds. Over here I need to be thinking powers of x. I have the constant term, a linear term, and a quadratic term. Degree 2, degree 1, degree 0. So let's divide these two whole numbers and then see if we can think of a way to divide these two polynomials. So we start by thinking to ourselves, well, how many times does 21 go into 46? And so we think, well, probably 2 times. So 2 times 21 is 42. And then I need to subtract. I'm left over with 4. And then I bring down to 3. I think to myself, well, how many times does 21 go into 43? Well, 2. And now I know I'm done because this value is less than 21, so 21 doesn't go in here anymore. And I'm left with a quotient and a remainder. And another thing I could think about is what we really know now is that 463 divided by 21 is 22 and 1 out of 21. And so I could use this long division to rewrite my improper fraction as a mixed number. All right, so let's see what I can do over here. I saw how many times 21 would go into 46 because I wanted to get rid of as much of that as I could. Over here, I need to organize my work by degree. So instead of thinking about just over here, I'm just trying to get a big number under here, as big as I possibly can without going over 46, I need to adjust my thinking just a little bit. I need to think about multiplying 2x by something to get 4x squared, because I want to get rid of the 4x squared. That's really my goal. And so I think, well, 2x times 2x gives me that 4x squared. So now I need to multiply, and I need to think about distributing. I'm going to take the 2x and multiply it by 2x plus 1. So I get my 4x squared, I get a plus 2x. And now I mimic what I did over here, and I need to subtract. But I need to remember to subtract everything. So I need to remember this minus is going to distribute. And what I usually say is that I change all of the signs to subtract. So now I have 4x squared minus 4x squared, and those cancel out. And when I'm dividing polynomials, that's always going to happen. That first thing is always going to cancel out if I've done everything correctly. And then, let's see, 6x minus 2x is going to give me a positive 4x. And now I need to bring down the 3. All right. Oop, need a plus in there. Oop, 4x plus 3. Now I want to multiply 2x by something so that I get exactly 4x. Well, that's 2. And again, I need to distribute, so 2 times 2x is 4x plus 2. And now I need to change all the signs to subtract. The 4x's cancel, and again, by design, that should happen. 3 minus 2, and I get a remainder of 1. And so here's my quotient. And here's my remainder. So I could think about it in the same way. The polynomial 4x squared plus 6x plus 3 all over 2x plus 1 is equal to my quotient, 2x plus 2, plus 1 over what I was dividing by, the remainder over what I was dividing by. All right, so there's long division of a polynomial. Let's do another example. So here, we're asked to divide x cubed minus 2x squared minus 3 by x plus 1. So I'm going to set up my problem under a division symbol. But I noticed that there's no x to the first power, so I'm going to write one in there. This is called a placeholder. When I'm doing long division of polynomials, I always need to see every possible power of x under the division symbol. So 3, 2, 1, 0. I see every possible power. Now, I've actually written this a little incorrectly. The problem I actually want to do has an x squared plus 1 in it. So if you would, just sneak back up to the original problem, put that square in there. I have x squared plus 1. I need placeholders under the division symbol, but I really don't need them outside of it. But what I tell students is, if you're having trouble remembering the placeholders, put them everywhere. You could sneak a 0x in there and it wouldn't hurt anything at all. So we do need to remember placeholders under the division symbol. Under the division symbol, which I should write out the words, but that's okay. So another way to think about that, this is a cubic polynomial on top, 3, 2, 1, 0, every possible power of x, up to and including the degree. Okay, let's do our division. I need to know how many times x squared goes into x. I like to think about that as, what do I multiply x squared by to get an x cubed? And that's an x. And just like in our last example, and I didn't mention this before, but every time I have something on here, I line it up over the correct term, right? This is an x to the first power, so I put it over the x to the first power. So x times x squared gives me that x cubed plus x. I need to change all of my signs to subtract. These cancel off. When I subtract, I end up with that 2x squared minus x. And now I need to bring down the minus 3. I need to think about what I multiply x squared by to get that minus 2x squared. Well, that's going to have to be a minus 2. All right, so I end up with that minus 2x squared minus 2. And now I need to change all of the signs to subtract. These cancel out. I end up with a minus x and a minus 1. Here's my quotient. And here is my remainder. All right, well, what I wanted to do about this one is talk about why I know this is the remainder even though it still has an x in it. In my first example, my remainder was a number, right, a constant. Well, it turns out my remainder always has to have degree less than my divisor, what I was dividing by. This has degree 1, this had to have degree 0. I know this is my remainder because it has degree 1, and what I was dividing by, my divisor has degree 2. My remainder here could be degree 1 or degree 0, but the minute I have anything less than this, I know I can't do any more division. Let's do one more example together. I want to divide 2x squared minus 4x plus 5 by x minus 3. No placeholders in this one because I see every possible power of x, but I always check 2, 1, constant term, that would be x to the 0, and I'm dividing by x minus 3. I need to multiply x by something to get that 2x, so that's going to, that 2x squared, so that'll be 2x. 2x times minus 3 is that minus 6x. And now I need to change all the signs to subtract. Minus 4x plus 6x is 2x. Bring down that plus 5. I need to multiply x by something in order to get that 2x. So that'll be a plus 2. 2x minus 6. Change your signs to subtract, and we get a remainder of 11. So my quotient and my remainder. And again, I know that's my remainder because this has degree 0 and I was dividing by a degree 1 term. In the next video, we're going to see an example of what's called synthetic division, and we'll do it do this problem actually again in that video using a different method.